Okay, starting the class, children. So last time you remember we did this disproportionation reaction. What is a disproportionation reaction? Any one of you? A disproportionation reaction. We did the balancing of redox reaction. Remember last time we did balancing redox reactions by half reaction method. We discussed all these points. Then we practiced some questions in the last class. Then I discussed with you this disproportionation reaction, in which this chlorine gas Cl2 in the alkaline condition is getting Cl2 in the alkaline condition is getting oxidized and reduced. The same element, element of the same substance Cl2. One is getting oxidized, other one is getting reduced. Same element is getting oxidized and reduced. That is a disproportionation reaction. Now, this is also an example of disproportionation reaction, this one. So can we work on it? So let's start. P4. What's the oxidation number of P4? What's the oxidation number of P in P4? Yeah, very good, Dhruv. Here it is 0. Now let's see the change. P4 to PH3. What's the oxidation number of P here? Oxidation number of P here. Hydrogen when bonded to? No, Dhruv. No, Shrihan. Hydrogen when bonded to non-metal, it is +1. So it is -3, isn't it? Check the rules, oxidation number rules. Hydrogen when bonded to non-metal. So there are two situations. When hydrogen is bonded to a metal, then hydrogen is -1. When hydrogen is bonded to a non-metal, then hydrogen is +1. Here P is non-metal, so it is -3. What about this one? What's the oxidation number of P here? Again, follow the rules. There are two hydrogen, so 2 times +1. P, I don't know, so I'm going to take it as X. Oxygen, I know, oxide is -2. From the periodic table also you can predict. Is equal to this charge -1. So what is X? Can you calculate X here? Is it? I'm getting +1, not +5. Right? Oh, yes, Sanjana, you're right. Dhruv, see the mathematics? Okay, so here now see the change. This P is +1. This P is -3. P4 to PH3, what is it? Reduction, oxidation? P4 to PH3 is gain of electrons, right? So it is reduction. Decrease in oxidation number. P4 to H2PO2 minus. What is it? Reduction, oxidation. This is oxidation. So the same substance, the element of the same substance, P, is undergoing reduction and is also undergoing oxidation. So we can call it as disproportionation reaction, right? So this is also one of the important example of oxidation reduction reaction. Now today we are going to do balancing of redox reaction using oxidation number method. Okay, children, here you can see all the rules are written. So what I'm going to do that I can give you these rules in the chat. You can take out the printout if you want. Okay, rules are here in the chat. You can see the rules on the website also in my notes. Okay, so ready? Let's pick up one equation. This one or this one? Which one you want to pick up? I think we should go for this one. Aluminum permanganate, manganese dioxide, aluminum hydroxide. Okay, let's take this equation. We'll try to balance this equation by using these rules. So first rule, write unbalanced equation. So aluminum plus permanganate, this one, this is permanganate ion, giving you manganese dioxide plus aluminum hydroxide with 1 minus. This is unbalanced equation. Now rule number 2, assign oxidation number to each element. So what is the oxidation number of this aluminum? Yes, please answer here. 0. Get the oxidation number of manganese. Oxidation number of manganese. Assume it as X. Oxygen you know is -2. So X plus 4 times -2 is -1. So Dhruv is right. It is +7. What is manganese here? This one. This manganese. Use the same rule. X plus 2 times -2 is 0. It is +4. What is aluminum here? Do you know the charge on OH, children? Any one of you know the charge on OH? Any one of you? Yes, -1. So how many OH are here? 4. You can work out why this charge is -1. Because oxygen is -2. Hydrogen is +1 with oxygen. So it is -1. It's a very popular ion. All the bases, metal hydroxides, they have OH. So now work out the oxidation number of aluminum. Aluminum is X. OH is -1. How many OH? 4. 4 times -1 is -1. Yes, so it is +3. So rule number 2 is done. Assign the oxidation number to every element. And now balance these atoms which are undergoing change in oxidation number. Rule number 3. You see, I didn't check for oxygen and hydrogen because they are not changing. Here it is -2, here it is -2. So I didn't check it. So I just checked aluminum and manganese because they are the one which are undergoing a change in oxidation number. So you have to check who all are undergoing change in oxidation number. Whoever is undergoing change in oxidation number, you're going to write on the top the way I have written. This is 0, this is +7, this is +4, this is +3, right? Now, rule number 3. Valence atoms undergoing change in oxidation number. What does it mean? It means balance your aluminum and manganese. Are they balanced? Number of atoms. Are they equal on both the sides? One aluminum here, one aluminum here, one manganese here, one manganese here. So they are balanced. So rule number 3 is done. Is it okay? Okay. Now determine the factor that will make the total increase and decrease in oxidation number equal. Before that, I think I'll add one more rule here. Calculate valence atoms undergoing a change in oxidation number and calculate the transfer of electrons. Transfer of electrons. So aluminum 0 to aluminum 3 plus. How many electrons? Aluminum 0 to aluminum 3 plus. How many electrons are given? This is oxidation, right? So how many electrons are transferred? 0 to 3 plus? 3 electrons. Manganese plus 7. Check here. Manganese plus 7 to manganese plus 4. Plus 7 to plus 4. How many electrons? Plus 7 to plus 4 is gaining 3 electrons. It's reduction, right? Decrease in oxidation number. So this rule is saying check the decrease and increase in oxidation number and equalize them. Like here is losing 3 electrons. This one is gaining 3 electrons. So everything is perfectly done. 3, 3, same. So rule number 4 is also done. 3 electrons are lost and 3 electrons are gained. So I'm done up to rule number 4. Now rewrite the equation. Because you see I have done so much work on the equation. So let's write down neatly. Now there is no need of writing these oxidation numbers. So I'm writing neatly the equation, whatever work I have done till now. MnO2. In fact, there is no change. OH4 minus. So this is the equation which is appearing now. Okay. Now what's the next rule? Balance the charges by adding H plus or OH minus. Let's say I'm asking you to balance this equation in basic medium. Basic. So I have to balance the charges by adding OH minus. How much charge on this side? And how much charge on this side? Yes, children, how much charge on this side? You remember how to balance charges? -1. And how much on the other side? -1. Charges are equal. So I need not to do this thing also. This equation is very simple. We are not doing anything till now. Everything is coming out equal on its own. So this point is done. But now I have to balance hydrogen by adding water. How many hydrogens on the right side? And how many on the left side? 0. So how much water should I add on this side? How much water on this side to balance hydrogen? No, we are not adding H plus. We are adding water. We are on rule number 6. Okay, we are not adding H plus. We are adding water. So I'm going to add 2 H2O. Now check oxygens. Check whether your oxygens are equal. Check oxygens on this side, on the left side. 2 plus 4, 6. This 2, 4. And how many on this side? So it means we have not done any error in balancing of the equation. And this is the perfectly balanced redox reaction using oxidation number method. Is it okay? So now I'm giving you another equation. But let's simplify the rules, easy to memorize type. Okay, I'm giving you rules from my side. Rule number 1 is unbalanced equation. 6 is the number of oxygens. Dhruv, 6 is the number of oxygens on both sides. Check oxygen on this side. Check oxygen on this side. 6, right? Okay, now we are going for rewriting the rules in very simple abbreviated form so that you can easy to memorize type. So write unbalanced equation. Rule number 1 stays the same. Rule number 2, assign oxidation numbers. Assign oxidation number. This is rule number 2. Rule number 3, balance. B for balance. Balance atoms undergoing change in oxidation number. Undergoing change in oxidation number. This is rule number 3. Rule number 4, equalize. Not equalize, you can first write calculate number of electrons transferred. One is undergoing oxidation, other reduction. So we have to check how many electrons are transferred and equalize them. I show you how to equalize. Number of electrons gained and lost must be equal. These are 4 rules. Rule number 5, rewrite the equation. Means after doing all these things, now whatever is there, rewrite it neatly. Rule number 6, check charges, balance charges by using H plus or OH minus. H plus acidic condition, OH minus basic condition. So you have to check what condition is given. Then accordingly you will use and balance the charges. Rule number 7, balance hydrogen by adding water. So these rules are different from half reaction method. Rule number 8, check oxygens. If oxygens are equal, then it means you have not done any error. Ready, Lasya? So I'm writing here. Srayu, you're there? Yeah, okay, you're understanding? So try to answer here also, right? So ready for one equation? CrC2O4 2 minus plus MnO4. Initially, I wanted to give something else, but now I've decided this. This is oxalate ion, giving you CO2 and Mn2 plus. Balance this equation in basic medium. Basic. Ready? Follow the rules. Rule number 1 done. Rule number 2, assign oxidation number. So what's the oxidation number of carbon here? Yes, all of you please. You can assume it as X. So 2X, there are two carbons, plus 4 times. Very good, Saranya, very good. 4 times minus 2 is minus 2. So children check Saranya is right. See, this is how you're going to do mathematics. Isabella, like this. Get the value of X. Yes, plus 3. And what is here on the other side in carbon dioxide? So this is plus 3. What is here? Here in CO2. Calculate. Yes, plus 4. Manganese. Work out manganese, children. Same method. You can assume X. Saranya, check again. You're talking about this manganese, permanganate manganese. Saranya, it is plus 7. See, manganese is X. 4 times minus 2 is minus 1. Get the value of X. Very good. And this manganese is already as a monoatomic ion, so it is already plus 2. So assign oxidation number done. Oxygen is not showing you any change in oxidation number. It's minus 2 on both the sides, so I didn't assign it. Rule number 4. Calculate number of electrons transferred. Remember, but before that, rule number 3, sorry. Rule number 3. Balance atoms undergoing change in oxidation number. So atoms which are undergoing change in oxidation number, they are carbon and manganese. Check. How many carbons on this side? How many on this side? So what should I do? I'll put 2 here, 2 CO2. I'm balancing the atoms undergoing change in oxidation number. Manganese are okay. This is very important. You have to follow it exactly in the same way. Do not try to break it. Follow exactly in the same way, right? Okay, now you have your rule number 3, 2, 3 is done. Now we have rule number 4. Oxidation numbers are written here, plus 3, plus 4. So how many electrons from plus 3 to plus 4? What is it? Oxidation, reduction. Plus 3 to plus 4. How many electrons are transferred? Saranya, we are not going to balance oxygen till last. In the last, we are going to check it. Do not worry about anything else. Follow the rules. That's it, step by step. Do not worry about oxygens, about hydrogens. Okay. 1 electron, I agree. This is 1 electron, plus 3 to plus 4. But how many carbons are here? So can I say 2 times 1 electron? 2 carbons. So 2 electrons, correct? Take care of this number. Each carbon is plus 3. Is going from plus 3 to plus 4. Each carbon is losing 1 electron. So 2 carbons will lose 2 electrons. And this is oxidation. It's losing electrons. Any doubt here? Okay, now let's go for the permanganate from plus 7 to, this is plus 7, to plus 2. How many electrons? Plus 7 to plus 2. Is it gaining or losing? There is a decrease in oxidation number. Yes, 5 electrons gained. 5. These two numbers are equal. This 5 and this 2. Rule number 4. Calculate the number of electrons transferred and equalize them. Are they equal? If you see, one is giving you 2 electrons, this is 2 electrons, and this is 5 electrons. They are not equal. I have to make them equal. So, do you know any factor which can make them equal? What's the common factor of 5 and 2? 10. Common multiple, right? So, what I can do? I can multiply this equation by 5. This one, oxidation. So, I'm multiplying it by 5. Children, see here. 5 here. So, this will become 10. Agreed? So, I multiplied the oxidation reaction by 5. Only oxidation. So, I placed 5 in front of this and 10. Now, this has become 10 electrons. And what should I do with permanganate? I multiply this by 2. This is also 10 electrons. So put 2 here and 2 here, right? So we are done. Step 1, step 2, step 3, step 4. Now rewrite the equation. Rewrite the equation. Because you see, so much work is done. So I'm not going to write the extra things. I will just focus on the equation and I'm writing it. 5 C2O4 2 minus plus 2 MnO4 1 minus giving you 10 CO2 plus 2 Mn2 plus. We are comfortable? Now everything is neatly written so that we should not get confused with oxidation numbers and the charges. Now the next step, balance this, rewrite the equation you cannot see in the books. Even your teachers will not tell you this. This is from my side because I have seen that if we keep working on this, it will be so confusing. So neatly take out your equation, whatever you have balanced here. Balance charges by using H plus or OH minus. I'm giving you the condition here for this equation basic. So I'm going to balance by using OH minus. Check. How much is here? Charge, total charge. 5 times 2, 5 times 2, minus 10. 2 times minus 1, minus 2. So minus 12. Sanjana, you are getting it? How I'm calculating it? Sanjana. And how much is on this side? 2 times plus 2. So plus 4. So how much OH minus? Yes, Ashita, good. How much OH minus I should add on which side? OH minus will increase the negative charge. So definitely you will add it on the side of positive charge, right? Negative has to be added on the side of positive. Now I have to make this charge as minus 12. So 16. Okay, good. 16 OH minus. Good. We are done with the rule number 6. Okay, now let's work out the rule number. Okay. Now let's work out the rule number 7. Balance hydrogen by adding water. How many hydrogens on which side? 16 hydrogens on this side, right? That's it. So I will add 8 water, right? 8 H2O on the left side. Now hydrogens are balanced. Now you have to check oxygens. Check oxygens. How many oxygens? 8. I'm writing here 8 due to water plus 5 times 4 due to this one plus 2 times 4 due to this one. How much is this? 28, 36? Yeah. Check, do we have 36 here? 10 times 2 due to this and 16 from there, 36. No error. So children, are we okay? So this is your completely balanced equation. There is no error when I'm checking the oxygen. See, oxygens are balanced, hydrogens are balanced. So what is the sequence? The sequence is first you write down the unbalanced equation. Check change in oxidation number, assign oxidation number. Calculate the number of electrons which are needed to be transferred. Make them equal the way we did here. 5 times 2, 2 times 5. Make them equal by using some factor. Then once you are done this, rewrite the equation. Now check the charges. If it is acidic condition, add H plus. If it is basic condition, add OH minus. Then check hydrogen, balance them by adding water. Then in the last, check oxygens. Oxygens should get balanced on their own. Okay, ready for another? One last equation. This we have done already, children. Can we balance this one? Okay. So unbalanced equation done. Rule number 1 is done. Keep checking your rules. Rule number 1 done. Assign oxidation number. Yes, who is going to help me? What is the oxidation number of lead here? What is the oxidation number of lead here? Mm-hmm. Plus 4. What is the oxidation number of lead here? Yes, Shriyan. What's the oxidation number of lead here? You know the sulfate, children? Sulfate. See from here. Can you predict the charge on sulfate? Yeah, it is plus 2. See, predict the charge on sulfate from here. Sulfate has combined with 2H plus. 2H plus. So what is the charge? 2 minus. Number of hydrogens in the acids can give you the charge on that polyatomic ion. Like if I give you H3PO4, what's the charge on this phosphate, children? What's the charge on phosphate? 3 minus because it has combined with 3 hydrogen. Each hydrogen is 1 plus. So it means phosphate is 3 minus. Isabella, you're understanding this? Making of the formulas, right? Okay, so what's the oxidation number of sulfur here? Any one of you? H2SO4. Hydrogen, there are 2 hydrogen. Each hydrogen is plus 1. Sulfur, I don't know. So I'm taking it as X. 4 times minus 2. Oxygen, 4 times minus 2 equals to 0. So what is it? What is X here, children? No, no, Sanjana. Check it again. X is plus 6. In this acid, in this formula unit, only oxygen is negative. Rest all are positive. Only oxygen is the one which is more electronegative. You can see from the periodic table. So here sulfur is +6. Is there any change in the sulfate? Is there any change in the sulfate on the left side and right side? No, there is no change. See sulfate here. You check the oxidation number, you'll get +6. So oxidation number of sulfur is not changing, right? We are on rule number 2. We are assigning oxidation numbers and we found oxygen and sulfur and hydrogen. Hydrogen is not there. So it means hydrogen is not undergoing any change in oxidation number. Oxygen is not undergoing any change in oxidation number. Sulfur is not undergoing any change in oxidation number. So who is undergoing change in oxidation number? Which element is undergoing change in oxidation number? Mhm. Lead. Yes, Sanjana. Good. What about rest of you? Sarayu? It's written here. You can check. This is 0. This is +2. This is +4. And this is +2. So Pb is undergoing oxidation and Pb is also undergoing reduction. So what is the rule number 3? Check the rule number 3. Balance the atoms undergoing change in oxidation number. So please balance your lead. How many leads? How many leads, children? On this side, how many are there? Wait, Shrihan. Why? I'm asking you to balance the number of atoms. Balance the atoms undergoing change in oxidation number. Look at the rules. You have the rules? Yes. What about rest of you? Understanding? It's 2 here. Are we good? Okay. Now, what is the next rule? Calculate the electrons transferred. So this Pb to Pb, how many electrons? From 0 to +2? It's only one Pb, right? So one Pb to Pb2 plus Sarayu. How many electrons are transferred? Is it oxidation, reduction? Pb0 to Pb +2. How many electrons? 2 electrons, and it is, what is it? Oxidation, yes. +4 to +2 here. +4 to +2. How many electrons? 2 electrons. Check. These 2 electrons lost and 2 electrons gained. I don't require any factor, right? My number of electrons transferred are equal. So I'm done up to rule number 4. After rule number 4, I said rewrite the equation. Remove all these lines. Rewrite the equation. Pb plus PbO2 plus H2SO4 giving you 2PbSO4. I have rewritten the equation neatly, right? Now, the next step, balance this equation. Can you predict the condition here? Can you predict the condition? Acidic. We are using sulfuric acid. So condition is already acidic. So I am going to balance the charges. Rule number 5, balance the charges. How much charge on this side, children? Charge, total charge on this side. Mhm. Charge on this side. What is the charge on Pb? Is 0, yes. What's the total charge on this side? Is again 0. Do I need to balance the charges by adding H plus? No. Charges are equal, right? Okay, charges are equal. So now I'm on the next step, balance hydrogen by adding water. I need to do that. See here. Two hydrogens. So I need to add one water on the right side. Now hydrogens are balanced, right? Now the last step, check oxygen. Can you tell me how many oxygens are here on the left side? Left oxygens. 6. Right oxygen. Oh, so it means we have done some error, children. See, oxygens are not balanced. Right, you are saying 9. Yeah. Left, we are saying. So what's the error we have done? Yes, we have to balance the sulfate also. Correct. Dhruv, thank you very much. This should be 2H2SO4. Then this should be 2H2O because sulfate has to be balanced. Sulfate is actually spectator ions here, but we need to balance them, right? So how many oxygens now on the left side and right side? They are 10 and here 10. So once you are doing the last step, then because sulfate we didn't consider anywhere, then at that time the way Dhruv analyzed that there should be 2H2SO4 because there are two sulfates. So in the rule, nothing is written about sulfates. Then we can do this kind of balancing also. We can analyze and we can put the numbers to balance the other atoms in the last. And then we can check oxygens. Very good, Dhruv. So are we clear about it? So that's the balancing of redox reaction by using oxidation number method. Children, there is one topic we call it as titration. Titration is nothing but a reaction. I'm not covering this topic here in this unit. I will cover this topic with unit 8. Okay, because it is more in detail in unit 8 when we are going to do acid-base titration curves also. Otherwise, it's just a chemical reaction. So we'll discuss more in detail in unit 8. So you can leave the quiz of titration. Okay, now we are ready to start the new topic. Topic 5. Very easy. You can memorize it, you can practice it with me only because I will be teaching you this unit only with the help of questions. We'll do questions and questions. Try to memorize it. I have seen that my children, my students from last so many years, they become very good in kinetics. They never lose a mark, a single mark in kinetics. So it means you can learn it during the class, practice it, do the quizzes, and you'll be good. Right? So kinetics. First, let's try to understand the word kinetics. Kinetics means, unit 5 we are starting. Kinetics means motion. And what this motion is doing in chemistry. In chemistry, kinetics is you're learning to understand how fast or slow a reaction. Some reactions are very explosive. Some reactions are very slow. They need years and years to happen. So reactions are very fast. They can take place within microseconds. Reactions are very slow. They need plenty of time. So kinetics is going to make you understand that. You will understand the fast and slow means you are measuring time, how much time, right? So this we are going to understand in terms of rates of reactions. So in kinetics, you will be learning rates of reactions. So the topic kinetics is dealing with rates of reaction, why this reaction is fast, why this reaction is slow, and what happens if I increase the concentration, what happens if I increase the temperature factors. So all these things we are going to do, rate laws, integrated rate laws, mechanisms of the reactions, elementary steps, activation energy. So it's a very important topic and is going to be the part of unit 6 also. So unit 5, some part like activation energy, it is there in unit 6 also. So kinetics means how fast or slow a reaction. When I say fast and slow, it means I'm talking about time, which I'm going to measure during a chemical reaction as rate of a reaction. So let me tell you the meaning of rate of a reaction. Let's say A is giving you B. This is the reaction. And let's make a graph. Concentration versus time. So as the reaction is proceeding in the forward direction here, like this, what is happening to the concentration of A, children? What is happening to the concentration of A? Is it increasing or decreasing with time? A is the reactant. I hope you're understanding this. It's decreasing. Very good, Isabella. So it's decreasing. So I'm going to draw it like this, is decreasing, right? And what is happening to the concentration of B with time? Concentration of B is increasing. B is the product. As A decreases, B increases. Correct? Okay, now rate. Rate is defined as rate is defined as change in concentration. Change in concentration of A or B over time. Whatever time is taken to change that concentration over time. Time taken. So let's write down proper definition here. Rate is defined as change in concentration of A or B over time. Time taken. And rays are generally with, they are never with the negative sign. They are always with positive sign. They have to be with positive sign. So the rate is change in concentration per unit time. How to represent it? Minus for A. Why? Because A is decreasing. Final is less than initial. So minus delta A over delta T. That's the rate. Decrease, minus means decrease. Decrease in concentration of A. This is concentration, remember? Square brackets. It means this concentration is in terms of molarity. This concentration is in terms of molarity. Remember molarity word? Molarity is moles per liter. How many moles per liter? So decrease in concentration of A. Decrease in concentration of A. This minus indicates that A is disappearing. Disappearing means decreasing, getting converted into B. Delta means change, final minus initial. This delta means again change. So this is rate. What are the units of rate, children? Units of rate. Numerator is molarity. Denominator is seconds. So the units of rate is always molarity per second. Or you can write moles per liter per second. You can write like this also, right? So, is the word rate clear? Rate is change in concentration of the reactant or of the product. Here I defined it in terms of reactant. I can define it in terms of the product also. Delta B, delta means change. Square means concentration, molarity over delta T. Unit here also the same, molarity per second. But why I'm taking plus here, children? What is the reason I'm taking B as plus and A as minus? Any one of you? Why I'm taking B plus? Look at the graph. This is B because B is increasing and A is decreasing. That is the reason. Yes. B is increasing, so you are going to take it as plus. A is decreasing, disappearing, so you are going to take it as minus. Is this clear? Okay. So today I'm starting with collision theory. Though it comes in the last, in the quizzes also, it is, I think, in the last only, but I prefer to make you understand first and then we'll move for the rate laws, integrated, rest all is mathematics. This is something which we need to understand. Which unit, Dhruv? Collision theory? No, collision theory will come again and again. Here you are going to learn it in a different manner. You were in the other group earlier, you remember? That's why you're saying this. So, collision theory. What is collision theory? Understand this. It's very easy. Very, very easy. When there is a chemical reaction, please listen to every word because if you miss sentences, then you won't be able to relate what I'm saying. It's a very simple thing. Let's say there is a reaction, NO reacting with O2, giving you NO2. Balance the equation. Is it balanced? Yeah, right? Okay. Now, when this reaction is taking place, NO must collide with O2. Agreed, children? They must be collision. They must collide. They are gases, all of them right now. I've taken them in the form of gas because gases have high kinetic energy. No, I changed the page. Children, can you see this collision theory, the title? What happened? Is it now there? Okay, fine. So we are doing collision theory. So I'm writing the equation again. NO plus O2 giving you NO2. This is a very popular reaction. It helps in the fixation of nitrogen in the soil as nitrates. You know, nitrogen is the part of proteins. From where we are getting this nitrogen in the plants, in the proteins? From the air. You know the sequence of the reaction? N2, nitrogen gas in the air, reacts with O2 in the air. During this thundering and lightning raises the temperature. The temperature is very high. When you see the lightning, thundering, at that time, temperature of the clouds where it is happening is very, very high, very high. So their N2 reacts with O2, which is so unreactive. At that time, it gets converted into NO. Now this NO to NO, this NO reacts with O2 further to give you NO2. This NO2 reacts with water and oxygen again, half O2 we can say, giving you HNO3. You can balance the equation. Then this HNO3 is coming and getting mixed with soil. In the soil, this nitrate is completely soluble in water. Rule number 1 of the solubility rules. In the solubility rules, unit 4, we decided that nitrates are always soluble. These nitrates, which are coming in the form of acid rain, the nitrates are getting completely dissolved in water. And they are the part of the salts now. And is soluble in water is taken by the plants. And there these nitrates, they become the part of your proteins. This is called as nitrogen fixation. Nitrogen fixation. It's very important process for the survival of life. Proteins are needed by plants, animals, everybody, right? So proteins are synthesized by plants. Then they are taken by the animals. Okay. So the reaction is 2NO reacting with O2 to give 2NO2. Now, during the reaction, what is needed? What is compulsory? Collision is must. They must collide. Collision is must. If they don't collide, then there is no reaction. If NO is solid, this is a gas, this is a gas, they are moving, they are present in the same container, NO and O2. So they must collide. Without collision, no reaction. If let's say this can be a question. If let's say I give you NO solid, O2 solid, do you think reaction will take place? If both the reactants are solid, do you think reaction will take place? A solid plus B solid. Will there be any reaction? Is this the answer, Sanjana? No reaction. No reaction. Why? Because they are not moving. If they are not solid, if they are not moving, then they will not collide. If they don't collide, no reaction. So collision is must for a reaction to happen. Is it okay? The molecules must collide. If they are in the solid form, then all of them are in the solid form. One of them is solid, other is liquid. Still, the liquid will come and collide. But if all of them are in the solid form, no reaction, right? Second, when they are colliding, now look at this NO and O2. If you look at the Lewis dot structure of these molecules, they are chemically bonded like this. These are the reactants. Reactants. So when they collide, during the collision, they should have sufficient amount of energy to break the bonds. Bonds will break, right? The reactants, all the bonds will break for the reactant. So when the bonds will break, energy is needed. Agreed? Bond breaking. Bond breaking is, write down, this is a very important concept. Bond breaking. Bond breaking is attraction making or attraction breaking. Bond is attraction between two atoms, chemical bond. So when you are breaking a bond, you are breaking Attractions. Yes. An attraction breaking, energy needed or energy released? When we are breaking attractions, energy is needed or released? Needed. It is endothermic process. Please write on this and memorize it. Endothermic. Bond breaking, attraction breaking is always energy needed. Endothermic. You know the word endothermic. Endo means in, thermic means heat. Is it okay? Now let's see this energy profile. So some children, they say they don't know the word energy profile. This is energy profile. This is the reactant. You can see the word reactant here. Reactant. This is the product. Very first step that we need to break the bonds of the reactant, right? This is reactant. We need energy. Energy. This is here is the energy, children, over here. Energy is needed. Can you see this? Is it okay? Energy is needed. The energy is needed means profile is going up, needed. This minimum amount of energy, this is minimum. If you don't supply this much energy to the reactant, this much. If you don't give this much energy to the reactant, no reaction. So they will collide with each other. Collision is happening, but still no reaction. Why? Because the collision doesn't have sufficient amount of energy to cross this barrier, the hill, the top of the hill. The molecules must go with high energy. They should cross this barrier, and only then they can make the product. Only then you can break the bonds. And when bonds are broken, then reactant will start getting formed. The product, sorry. Then the products will start getting formed. Children, is it too much? So can I say the next point? The molecules must have collision, must have collision, must have sufficient energy to break all the bonds in the reactant. Sufficient energy. We are clear? If this energy is not there, if let's say molecules are colliding, but the energy is only this much, this is the energy. Do you think you will get the product? No. Here, you will get the product? No. Here, yes. Or here, yes. It should be this much or more than this. Only then you can get the product. But what is the name of this energy? You can see the name here in energy profile. Activation energy. The minimum amount of energy which is needed to break all the bonds in a reactant is called as activation energy. Till the time you don't supply this activation energy to the reaction mixture, there will be no reaction. So this energy, collision must have sufficient energy. What is the name of this sufficient energy? Activation energy. So it means the collision energy must be greater than or equal to the activation energy. Agreed, children? Molecules, when they collide with each other, they transfer energy to each other. During collision only, bond breaking will take place by taking energies. Collision is a when somebody collides with another thing, like a car colliding with another car, you can see the damage. Collision is a energy transfer process. And if that energy is more than or equal to activation energy, then reaction will can happen. Reaction can happen, right? Is it clear? These two conditions. There must be collision. The collision must have sufficient amount of energy. Another important factor, the next important factor is proper orientation. Proper orientation of the collision. Now let's try to understand the meaning of proper orientation. NO colliding with O2 to give NO2. That's the reaction we are discussing, right? Let's look at the Lewis dot structure of NO2. There is nitrogen with oxygen here, and actually there is like this, and there is one electron, so it has a positive charge. So all these things we have done earlier. So this is the Lewis dot structure of NO2. And what is NO? Look at the NO. It is something like this. So I'm not counting everything. So I'm just giving you a random structure. If we just forget about these lone pairs and just look at these atoms, just focus on atoms. What collision is needed? Nitrogen, oxygen colliding with nitrogen, or oxygen colliding with oxygen? What collision is needed, children, to get this compound? Oxygen gas colliding with nitrogen or oxygen gas colliding with oxygen? Which collision is needed so that you can get NO2? Oxygen colliding with nitrogen. This is proper orientation, this one. This can give you the product, proper orientation. And this one, not effective. Not effective collision. You're understanding this? So in this container where NO, O2, they all are present together, they all are colliding, collision is random. Collision is not in your control. You are not holding NO and O2. You're not asking, okay, orient like this, now collide. No, no, there's nothing like that. Collision is a probability. This proper orientation of the collision is a probability, right? Because this you cannot control. But how can I increase this probability of proper orientation? I want to have more collisions with proper orientation. How can I do that? If I increase the number of collisions, when you are playing, you're going to hit something. So every time you're going to hit, and more you play, more are the chances that you will win. Correct? So same here, when the molecules are colliding, if you increase the number of collisions, then the probability of proper orientation will increase. And if the molecules have sufficient energy, proper orientation, if these two conditions are satisfied, then only you will get the product. These are called as effective collisions. So there are plenty of questions on effective collisions. What are effective collisions? The collisions with sufficient energy. What do you mean by sufficient energy? Energy equal to activation energy or more than that, and with proper orientation are effective collisions which can give you the product. Children, if you have any doubt here what I'm discussing, You can ask questions. So rate of reaction, rate means how fast, how slow, is directly proportional to the number of collisions. Because if you have more collisions, then there are more chances of proper orientation, and there are more chances of the molecules with more than with sufficient amount of energy, the energy more than activation energy, more chances, right? So I'm talking about the probability here. So probability can be increased if you increase the number of collisions, right? Is it okay? Fine. So what we have to take from here? One, this equation that rate is directly proportional to the number of collisions per unit time. More number of collisions, more higher the rate. But these collisions must be effective. So what's the meaning of the effective collisions? There are two conditions which should be satisfied for getting the product. The two conditions are sufficient energy and proper orientation during the collision, effective collisions. If these two conditions are satisfied, then you get the product. Is it okay? Okay. Now, are we clear about the activation energy here, children? Activation energy. This is the energy of the reactant. This is the energy of the complex, the transition state. We call it as transition state, activated complex or transition state. What is happening in the transition state? The bonds are breaking and forming. You know, you're supplying energy to break the bond. So bonds are breaking, chemical bonds are breaking, and new bonds are getting formed. Like for example, H2 reacting with I2, giving you 2HI. Now the transition state, I'm showing you the transition state. You are breaking the hydrogen-hydrogen bond, this one, and you are breaking the iodine-iodine bond. See, this is breaking. And new bonds are forming between hydrogen and iodine. This is called as transition state. The highest energy state of an energy profile. Energy profile means reactant to product, how the energies are changing. Reactant to product, the progress of the reaction. At that time, the first step is breaking these bonds and forming of new bond. So the highest energy state represents the transition state where the bond formation and bond breaking is happening. Is it okay? Both the things are happening here. Both the things. Bond breaking needs a large amount of energy, so you're on the top of the hill. Now bond formation has started. Once the bond formation has started, all the bonds are broken, then the reaction becomes highly exothermic. See here. This is bond formation, this one. The green one, exo, energy going down, energy going up. Are we clear? So on this energy profile, many questions will be there. Ready to answer some questions now? Okay. I'm giving you one energy profile here. This is the energy of the reactant. Let's say 100. And this is the energy of the product, let's say 50 kilojoules. It is in kilojoules per mole. Reactant is breaking bonds. Breaking bonds. Energy is going up. This is the top of the hill where the complex is formed, that transition state, bond formation, bond breaking. And then all the bonds are broken. Now new bonds are forming. Bond formation is exothermic. Energy is getting released. And finally, I'm getting the product here. So this is the progress of reaction, reactant to product. Progress of reaction. Is this reaction endothermic, exothermic? This is the energy of the reactant. This is the energy of the product. Is it endo, exo, this diagram? Yes. Why? Because delta H is HP minus HR. So how much is delta H? Because products have less energy. Yes, you're right. How much is delta H? HP is 50. You see energy, look at the energy profile. This is 50. HR is 100. So delta H is minus 50 kilojoules per mole. It means, what does it mean? What's the meaning of this negative sign, children? That this much amount of energy is released. Yes. Are we clear about this? This energy profile is for exothermic reaction because products have less energy than reactant. So it means exothermic. You can see how the products have less energy. Okay, now answer this question. If this mark is 150, answer this. What is this energy called as? This one. What is it? What is this energy called as, children? This one? From reactant to the top of the hill? Yes, it's written here also. Activation energy, you can write it as EA. EA, activation energy. How much is this? How much is the value? It is? No, 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 no. Okay. Yeah, this one is 100. Okay, fine. So it is 50 units, kilojoules, sign positive. Because activation energy is always the energy needed. It is energy needed to kickstart the reaction. Like when you are starting your car, you give ignition. What is that ignition? Why you are providing ignition? That's the activation energy you are giving to that petrol, the gasoline, to start combustion. If you don't give ignition, then no reaction. Ignition is very small amount of energy. It means gasoline is highly combustible. You don't require a very large amount of energy. Activation energy for combustion of gasoline is very low. So just a small ignition and it starts undergoing combustion. Okay, so we are clear about this energy profile. Now, I'm giving you another energy profile on the same diagram. This time, my reactant is here. And the product is here. Is this reaction endothermic or exothermic? What's the delta H of this reaction? The pink one, delta H reaction. Again, the same equation, HP minus HR. What is it? HP is this. HR is this. Is plus 50 kilojoules. Yes. Endothermic. How much activation energy for the pink reaction? How much? No, no, no. I think you're doing error, children. You have to start from this reactant from here, which is 50, and you have to go up to 200. So activation energy is 150. Now my question based on the collision theory. There is a question based on collision theory now. Very first question based on collision theory, which you have understood. Can you tell me which reaction rate will be faster and why? The pink or the green? The one with activation energy of 150 or the one with activation energy of 50? Which one is faster? Which reaction is faster? Shrihan has given his choice. What about rest of you? Which reaction will be faster? Because activation energy is the minimum energy, the sufficient amount of energy needed to start the reaction. And I said combustion of gasoline is very fast because you have to just ignite it. No, no, no. Nothing doing with exo and endo. Nothing doing with exo and endo, Dhruv. It has to be comparison of activation energies. In which case you need less amount of energy to kickstart the reaction. In which case? In the 50 kilojoules or 150 kilojoules? In the green one. So don't you think that less amount of energy means faster reaction, Isabella? Shrihan? So rate of reaction is inversely proportional to activation energy. High activation energy, slow reaction. Slow reaction or no reaction. Sometimes the activation energy is so high, slow reaction or no reaction. If activation energy is very, very high, then the probability that reaction will not take place because the collisions are not going to get sufficient amount of energy to give you the product. So a high activation energy means slow reaction or no reaction. Shrihan, is it okay? And low activation energy means fast reaction. We are clear about it? Lasya, where are you? You're understanding, girl? Ashita, Sarayu, Sarayu, how's your health today? Okay, good, very good. Saranya, your answers? Please understand this. It will be difficult to understand all these things using the book. Okay, good, Saranya. So, can I say activation energy decides the kinetics of the reaction? A very good important topic which will come in unit 6. Not unit 6, in unit 9, thermodynamically controlled and kinetically controlled reactions. It will come in unit 9. Activation energy decides the kinetics of the reaction. Can I say? Higher the activation energy, lesser will be the rate of reaction. Lesser the activation energy, faster is the reaction. So kinetics of a reaction are decided by the activation energy. We are good? But these are two different reactions. The pink and the green, two different. Activation energy for a particular reaction is fixed, constant. So write down this also. Activation energy, I'm talking about I'm making you familiar with activation energy. Activation energy is fixed for a reaction. It's fixed. So if you carry out a reaction H2 with I2, you change the temperature, you change the concentration, you do whatever you want to do. This activation energy will not change. Bond enthalpies, because activation energy is the energy needed to break the bonds. Bonds are not changing. Chemical bonds. Are you changing the chemical bonds? No. So chemical bonds are not changing. So activation energy will not change for a reaction. Nobody can change it. No one except one, which you have done in your bio also, and that's a catalyst. A catalyst can lower the activation energy. Only a catalyst. Very important topic going on, children. Activation energy, nobody can change for a reaction except a catalyst. So, what a catalyst can do to activation energy? It lowers the activation energy. And as activation energy goes down, what happens to the rate of reaction? It becomes faster. Agreed? So, this I'm just making you familiar with the activation energy. So, can you answer this question? What do you mean by effective collisions? Which collisions are effective? You know that molecules must collide and these collisions must be effective to give the product. So, what are the two conditions for effective collisions? Yes, Saranya, Sarayu, what are the two conditions for effective collisions? Mm-hmm. Isabella, Dhruv, Shrihan, the collision must have sufficient energy. This is the last time I'm telling you, children. No, sufficient energy. Do you remember the meaning of the sufficient energy? That collision energy, the energy must be equal to or greater than activation energy. It should be able to cross the barrier. This is the last time I'm telling you. Okay? During this kinetics, I will be asking you this question again and again. What do you mean by effective collisions? Which collisions are effective? Which collisions can give the product? Sufficient. And second, if you remember I was discussing NO, O2, O2 colliding from this side, O2 colliding from this side to give you, yes, proper orientation. Proper orientation. These are the two factors. If they are taken care, then yes, the product will form. Otherwise, no. So the proper orientation and sufficient amount of energy so that we can cross the activation energy barrier. Now, what do you mean by transition state? Transition state. Where is the transition state? Can you write down what is here? What is this? What is this? What is this? What should I write here? What should I write here? See, it's written here only. This is the energy of the reactant. This is the energy of the product. And this one is transition state. See, transition state. Transition state. Which you can write as TS. Transition state has the highest energy. because bond breaking and bond formation is taking place, right? Look at the reaction. BRNO colliding with BRNO. If they are colliding like this, then don't you think that you can get the product? If the collision is like this. Okay, let me show you other way around. 1 second. Let's make it other way around. This is BRNO colliding with BRNO like this, or BRNO colliding with BRNO like this. Out of these two collisions, which collision is effective? This is one. Which one is with proper orientation to give you Br2? Which collision can give you Br2? Collision 1 or collision 2? See, look at the product. Product is Br2. In the first collision, in this first one, the oxygen of the NO is colliding with Br, bromine. In the second collision, the bromine of the first molecule is colliding with the bromine of the second molecule. So Saranya is saying second. What about rest of you? Are you okay? The second collision is with proper orientation. And proper orientation is one of the conditions of the effective collisions. So this is effective, this one, right? Is this reaction endothermic, exothermic? This is exothermic, yes. So I think I told you less energy means more, less energy means more stable. Remember I gave you that mantra in chemistry. More attraction means less energy. Less energy means more stable. Check notes of unit that periodicity is written on the top of that document. If it is more attraction, if the molecules are more attracted, it means they are more stable. More stable means they have less energy. More attraction, less energy, more stable. So you are saying that this is exothermic reaction. So the product is more stable or the reactant is more stable? Which one is more stable, the product or reactant? Mhm. Which one has less energy here? The reactant or the product? Which one has less energy, children? The product. And the one which has less energy is more stable. This is called a thermodynamic factor. Thermodynamic. So in the thermodynamic, you know the word. You are doing in unit 6 is thermodynamics, thermochemistry. Unit 9 is also to some extent thermodynamic. Thermo means heat. So thermodynamic is talking about the energies of the reactants and products, not the activation energy here right now. Energies of products or reactants. So that's the one which is going to decide the stability, which one is more stable. Product is more stable in exothermic. Reactant is more stable in endothermic. Can I say that, children? Products are more stable in in exothermic. So write on this. Exo means products are more stable. Products are more stable. Endo means reactants are more stable. And this concept is based on that more attraction, lesser energy means more stable. Whoever has less energy is more stable. Whoever is with high energy is less stable, right? So now, what about activation energy? What activation energy is going to decide? The kinetics. Remember, I was using the word kinetics and thermodynamics. This term will come again in Unit 9. So activation energy will decide the kinetics, means it will tell you the fast or slow reaction, fast or slow. Whereas exo, endo will tell you who is more stable, the thermodynamics. Are you getting the picture now? So if you have any question, you ask. Otherwise, I'm going to put some questions here about which one is fast, which one is slow, which one is stable, which one is not stable. Ready? Okay. So here's a question on the concept which we have just done. I'm going to show you two energy profiles and we'll discuss about them. One, two, progress of reaction, reactant to product, progress of reaction. And you know that reaction is always going from reactant to product. So it means reactant here, product here. Same here, same thing here. And here is the energy. These are the energy profiles. Energy profiles. In one case, the reaction is in another case, the reaction is now you know that this is the reactant, this is the product, this is the reactant, this is the product, correct? We're okay with this? What is this, children, in both the cases? Yes, please answer. What is this? What is it? Activation energy. Yes, activation energy. What is this state called as? What is the state here called as? Transition state. And what is happening in the transition state? Bond breaking, bond formation. Good, Lassia. Bond breaking and bond formation. Ashita, you're okay with this? Transition state. Practice these terms because there are many questions on energy profile. And energy profiles are very important for understanding of organic chemistry also. So teachers, they are troubling organic children with energy profiles. And AP chemistry has introduced all these things very, I think around 2019 or 2020. Before that, they were not talking much about them. Okay, so we are clear about the transition state. We are clear about the reactant, product, energy, progress of the reaction, right? Okay, now my question. I'm asking you the kinetics of the reaction. Which reaction? Let's say this is reaction A, this is reaction B, So kinetics. Let's discuss the kinetics. Which reaction is slow? Oh, when I use the eraser, it disappears. Yeah. Which reaction is slow? A. Dhruv is saying A. A is slow. Why, Dhruv? You're right. Children, Dhruv is right. A is slow, but why? And B is fast. Can you give me the reason why, children? A is slow. What is the reason? Shrihan, it's a simple question, children. Because when you are discussing kinetics, oh, no, no, no. Sanjana, I'm not saying it's a combustion reaction. You have to give me the reason why A is slow. Because Dhruv, he looked at the energy profile, and from the energy profile, he said A is slow. And I said, okay, fine. Now Shrihan is writing. Yes, Isabella, Shrihan, very good. Perfect. So, Sanjana, what you have to see? Activation energy. I didn't specify the reaction. I didn't say it's a combustion or something else. So, from the energy profile, when you say slow reaction, the reason is activation energy. A is slow because of high activation energy. You need a large amount of energy to cross the barrier. So, molecules will be struggling for that energy. They won't be able to get this sufficient amount of energy very easily. So, reaction is slow because amount of energy needed, the sufficient one first condition for effective collision, sufficient amount of energy. That will be difficult to achieve. Sometimes these reactions are no reactions. Okay. B is fast. Why B is fast, children? I want all of you to type this reason. B is fast. Why? Yes, low activation energy. So what does it mean? It means many molecules, many molecules will have sufficient amount of energy to cross the barrier easily, faster, in less time. Correct? That's the kinetics. Now let's discuss the thermodynamics. The thermodynamics. Which reaction is giving you stable product? Reaction A, reaction B. We are looking up for stable product. B is giving us stable product. What's the reason? What's the reason, children? For the stable product, yes, Dhruv is writing. You have to see the energy of the product. This product has less energy. See, energy. This product has more energy. See, stable product means less energy. Less stable product means more energy. In which reaction the reactant is more stable? Try to answer, all of you. In which reaction, A or B, the reactant is more stable? Yes, Sanjana, very good. In A reaction. Sarayu, A reaction. Sarayu, when you answer here, you will learn better. Understand this. You will not undergo any distraction. Children, those who are answering here, I have seen their understanding is always better. I know that it's difficult to type and everything, but I'm not asking very long questions, just A, B, C. I know you people are very fast in social media. Tuck, 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 tuck. You type very fast, and I'm very slow there. I don't have any social media. I have this WhatsApp just for students. I don't have any Facebook, and I'm not very fast in typing. But all of you are very fast in typing. I know that very well. I've seen my children. So don't give me this reason that we are writing notes, so that's why we cannot answer. Srayu, are you there? You're listening, girl? So my request is answer here. Okay, just typing A, B, C, because I'm forcing you to think. When I'm asking question, I'm forcing you to think. And thinking is learning. If you think, decide, answer, then you are going to learn. Otherwise, no. So that's about the thermodynamics and kinetics. So can you tell me now one last question on these two energy profiles? Which profile is thermodynamically favored and kinetically favored? Thermodynamically favored means giving you stable product. Kinetically favored means giving you faster reaction. Which profile is thermodynamically favored? Which profile? Question is, which profile is thermodynamically favored? Thermodynamically favored means the product has less energy. You already decided that B, right? B. B is thermodynamically favored, stable product, right? See here. And which profile is kinetically favored? B again. So I can say B profile, B reaction is very effective, very effective, very fast, and giving you stable products. So it is kinetically favored. Oh, I'm writing. Kinetically favored and thermodynamically favored. Are we clear about these words, children? Kinetically favored means fast, low activation energy. Thermodynamically favored means stable products. So I explained you all these things just to make you comfortable with the word act, just to make you understand the word activation energy. Okay. Now we are working with the collision theory. Back to the collision theory, children. So what are effective collisions? What are effective collisions? Write the meaning of the effective collisions. We'll do this question in the last. Effective collisions. Write the meaning. Yes, I gave you two factors. Two factors. Sanjana, yes. First factor is right. Yes. Sufficient energy and proper orientation. In short, you can write like this. Sufficient energy and orientation. Yes, Isabella. Right. Sarayu, you're understanding this? Okay, good. Okay, now the factors. Because we are left with less time, so I'm going to discuss the factors very fast. Needs a hit where it needs to. That's the proper orientation. Yes. But energy is also important. If you are proper, if the collision is proper oriented, proper orientation is there. But still, product will not form if it doesn't have sufficient energy. Yes. Good. Shrihan. Okay, now because we are left with less time, so I'm going to tell you in brief with the with all of you are going to help me. This is a container. In this container, these are the molecules. They are colliding with each other. And the rate of reaction, we are going to discuss the factors affecting the rate of reaction. Let's discuss the first factor, temperature. So as you increase the temperature of the container, what happens to the kinetic energy, children? Unit 3, kinetic energy is directly proportional to temperature. So as you increase the temperature of the container, kinetic energy increases. But as kinetic energy increases, what happens to number of collisions? Number of collisions also increases. Molecules are moving faster, so they are colliding more. As they are colliding more, there are more chances of effective collisions. So as number of collisions are increasing, effective collisions are also increasing. Agreed? Effective collisions. Effective collisions, the one with proper orientation and sufficient amount of energy. So what is happening to the rate of the reaction? Rate of the reaction increases. This is the effect of the temperature. I'm going to discuss this more again in terms of distribution curves. Distribution curves also we did in unit 3. Maxwell-Boltzmann distribution curves. We'll do that. So higher the temperature, higher the kinetic energy, more is the number of collisions. Molecules are moving faster, so they are colliding more. They are moving faster with high energy, so the number of effective collisions are more, so the rate of reaction is more. So temperature. Second, concentration. The way I explained you this, can you explain me what happens when I increase the concentration? When I'm going to add more molecules? What happens when I add more amount? Yes, please. Yes. So when the concentration increases, concentration is more. Yes, please. More concentration, more collisions, isn't it? Agreed or not? More concentration means more number of collisions. More number of collisions means more effective collision. There is more probability of proper orientation. And there is more molecules can cross the activation energy barrier. More effective collisions. More effective collisions means more rate of the reaction. Is it okay? So first is temperature, then concentration. Third factor is, we can say, state of matter or surface area. State of matter, state of reactant or surface area. If I give you A solid with B solid, you can say no reaction, right? No reaction. Why? Because collisions are not there. But if I give you A gas with B gas, a fast reaction, fast reaction. Why? Because there are more collisions. Gaseous molecules have high kinetic energy. They are moving faster. Okay, Dhruv, no problem. They are moving faster, so their rate of reactions are very high. Collisions are more. So the state of matter, state of reactant is very important. We are good with this? The fourth is Catalyst. This is the last we are doing. The remaining we can do in the next class. Catalyst. What a catalyst can do, children, I told you in the starting, and the bio students, they already know. A catalyst, biocatalyst are enzymes. Enzymes are biocatalyst. So what a catalyst can do, it can lower the activation energy, E activation. It can lower the activation energy. So if I give you an energy profile, this is the activation energy. Reactant, product, energy here. And if I make it less like this is in the presence of catalyst when a catalyst is added. And this is without catalyst. So which reaction is faster? The reaction with less activation energy. This is what we were doing till now. This one has less activation energy, whereas the without catalyst has very high activation energy, right? So a catalyst is going to speed up the reaction, is going to increase the rate, speed up, speed is the rate, speed up the reaction. That's the definition we can see in the books. Or you can say increase the rate. Now you know the meaning of rate. Increase the rate by lowering the activation energy. So we are clear about it, children? So these are the 4 factors. There is, I think, one more factor which I'm going to discuss in the next class. So we'll start with these factors again in tomorrow's class. So if you have any questions, you can stay back.